Okay, so let's start. Hi everyone, I'm Ophir again, and today we'll have 3 sessions. The presentation will start with OpenMX. I would like to introduce Professor Ozaki from Japan, and Mr. Ozaki is leading this the application development in the University of Tokyo, and would like to share with you some of the to explain to you about the presentation and later discuss a bit about the tasks and open for questions. So can you try to share your screen, share the presentation?
Okay.
Okay.
Could you see screen?
Yes, we can see. Okay, go ahead. You can start.
Okay. Hello, everyone. So thank you very much for joining this my talk. So I'm Ozaki from the University of Tokyo. And first of all, I'd like to sincerely thank all of the organizers for giving this special opportunity to introduce our OpenMX code to the younger generations. So I'm wondering that some of you may not be familiar with the computational materials science. So I'd like to first introduce what computational materials science is, so that the student can be motivated to tackle the student cluster competitions. After that, I'd like to introduce the development of the OpenMX code, and I will introduce just one applications calculated by the OpenMX code, and I will touch the student cluster competition, and I will summarize at the end. So what is the computational materials science? So we are surrounded by the materials in our daily lives. So computational materials science is one of the most relevant subjects directly related to our daily lives. So you're touching any kind of the materials every day. So for example, suppose that we would like to develop the electric vehicles, EV cars. So in this case, we need to develop the high performance batteries, strong motors, which correspond to the development of the strong permanent magnet, and the light and strong body of the vehicles. They are all the issues in materials science, and computer simulations can provide us the guidelines how properties of the material can be improved. If you have the materials and would like to understand the physical and chemical properties of the materials, starting from the very basic fundamentals of physics, so we have to do the computational materials science. So this is a computational materials science. So I'm showing that some statistics to show the growing computational materials science. So this figure shows that the number of the papers to fit the computational method in our computational materials science field contributed. As you can see that the number of the papers keep increasing. Although this data is a bit old, but this data clearly shows that our communities is still growing. And also the 9 of the top 10 citation papers in physical reviews are on the computational materials science. So, which means that the what people working in these communities, computational materials science is quite extremely large compared to the other field. So this is the situation of the growing computational materials science in recent days. And let me remind you very famous words by the very old philosopher in Greece, Democritus. That is the atomic hypothesis. So Democritus considers that everything is composed of atoms, which are physically but not geometrically indivisible. So at this moment that we know atom can be decomposed furthermore, but in the sense that we are dealing with the conventional materials, actually the atoms is very fundamental, some particles consisting related to the materials. So with this basic ideas, actually we have already known governing equations for this kind of the materials consisting of the atoms. That is Schrödinger or Dirac equations. So Schrödinger equation is the very fundamental equations in quantum mechanics. The Dirac equation can be considered as a marriage between the quantum physics and special relativities. So this Dirac equation takes a bit complicated form as shown here. The psi is the wave functions. And so with these equations, we can predict the physical and chemical properties of materials. So almost all physicists believe that the systems composing of the atoms considered by the Democritus are described by these equations. So although that we know the governing equations for the materials, but solving these equations is a really hard task. So we have a couple of the conditions that the wave functions must satisfy. I'm showing again the Schrödinger equations here. So psi is the wave functions, h is Hamiltonians, consisting of the kinetic energies, the external potentials, and electron-electron interactions. So wave functions, which actually follows these Schrödinger equations, must satisfy the following conditions: indistinctiveness of electrons. So electron is not the classical particles. We cannot put the numbers to the surface of the electrons like very classical balls. So we cannot do that. So we should treat equal footings, such kind of electrons. That is indistinctiveness. And such a quantum object should have the very special statics, that is the Fermi statics. So from this Fermi statics, the wave functions follows the anti-commutation relationships. If we change the variables, if we properly write the wave functions, then the wave function actually changes the signs that correspond to the anti-commutation relationships. And sometimes we use these Paul's exclusion principles. So this is the equivalent to the anti-commutation relationships. Also, the wave functions follows these eigenvalue equations. So therefore, the wave function has also normalization conditions. So we need to satisfy such kind of the set of the mathematical conditions or the wave functions. So it's a really hard task. So in the overall sense, the computational cost to solve the Schrödinger and the Dirac equations scales as the order e to n's. So where the n is the number of the electrons in the systems. So you can imagine that the n is big numbers. It's not small numbers. So therefore, this computational complexities prohibit it to treat the large-scale systems, unfortunately. But we would like to calculate the physical and chemical properties of the real materials. Then we need to consider the another ways. So fortunately, several very genius people developed a couple of nice methods. Actually, the Nobel Prize in Chemistry 1998 was divided equally awarded to the Walter Kohns for his development of the density function theory, and John Poples for his development of the computation method in quantum chemistry. So actually, the method behind the OpenMX largely relying on this development of the density function theories by the Walter Kohns. And also the Nobel Prize in Chemistry is actually again awarded to the Karplus, Leavitt, and Walshaus for the development of the multi-scale models of the complex chemical systems. But today, I do not discuss these directions. So I would like to just focus on the development of the density function theories, because OpenMX is based on this density function theories. So let me explain very briefly what density function theory is. So 1964, Hohenberg-Kohns proves very famous theorems. Nowadays, we call the density function theories. They prove the following the statement: the energy of the non-degenerate ground state can be expressed by the function of electron densities. So our equations, Schrödinger-Dirac equations, are written by the wave functions. Then the energies should be expressed by the expectation value of such kind of Hamiltonians, which is evaluated by the many-body wave functions. But Hohenberg-Kohn could prove energies can be expressed by the energy function of densities instead of the wave functions. So this is a very big change of our views from the wave function to the density, electron densities. And many body problems, after this 1964, only the 1 year later, Kohn and Shams proposed a very nice, effective way to solve these ideas. That is now called the Kohn-Sham method. So their method is following. The many-body problem of ground state can be reduced to one particle problem with effective potentials. So this is the Kohn-Sham equations. And Kohn-Sham equations, Hamilton is expressed by the kinetic energy plus effective potentials. The effective potential has three contributions: external part, Hartree part, and exchange correlation part. And the non-trivial quantum mechanical effect are included in this exchange correlation functions here. So this change of the view from the wave function to the density, electron densities lead to the extremely large reductions in computational cost. So you have materials at hand. Then typically such kind of materials, any kind of materials, has this kind of large number of atoms, Avogadro numbers, 6 times 10 to 23 atoms. So it's really big numbers. If you work on Schrödinger-Dirac equations with the wave function theories, then you need to treat the variables 3 times n's. So you need to put this big number into the here's. So you can easily imagine it's really difficult problems. But once you change your view from the wave function to the density function pictures, so electron density is just functions of the real variables x, y, z. So therefore, the number of variables is only 3. So this is an extremely large deduction in the variables, 3n to the 3. So of course, we have some theorems, Bloch theorems. So with the help of the Bloch theorems, one can treat only the 3 variables instead of the 3n variables. So this is a very important step founded by the density functional theories. So, and also I'd like to remind you the development of the computers, so as well as the development of method. So for the last half centuries, computer powers keep increasing. So typically, the people discuss about this kind of top 500 figures, so which actually shows the Moore's laws. So this red one is the computational powers of the fastest computers at each years. Then at this moment, 2025, world fastest machines is El Capitan systems at the Lawrence Livermore National Laboratories, which has 1.7 exaflops computational powers. Then, based on these Moore's laws, one can easily extrapolate these lines. So I simply extrapolate it from the 2025 to the 2035. Then I can immediately notice that around the 2035, so computational powers may reach at here 1 zettaflops computational powers. Of course, the people also discuss Moore's laws will not continue anymore, but we don't know. Actually, this last half centuries, this Moore's laws was kept. So there was, I think, at least 10 years, still this extrapolation may be valid. So compared to the current computational powers, so 1 exaflops, about the 1 exaflops computational powers, so around the 2035, we may have the 1 zettaflops computation power, 1,000 times larger computational powers. So with this, some estimations, it's interesting to ask how large systems can be treated by the zeta machines. So performance increase is 1,000 times at this moment compared to this moment. Then we can easily estimate by considering the computational scaling properties or computational complexity of each method. So density functional theories, conventional density functional theory has the cubic scalings. So P is the 3, which is cubic scaling properties. Then we can estimate the computable size using the 1 zettaflops machines is 10 times larger. But if you look at the other, some wave function-based techniques, like a coupled cluster, single, double, plus triple excitation method, which has a P equals 7, or the N to 7. So therefore, even we have 1 zettaflops machines, computable size becomes only the 2.7 times larger. So applicability of the order n cubic DFT method is extended to the 10 times larger systems, which is better than the other method. So let me move on the discussions of the development of OpenMX code. So on top of the development of the density function theories, OpenMX actually has been developed. So OpenMX is the abbreviations of the open source package for material explorers, so OpenMX. So this is software package for the density functional calculation of molecules and bulks, and based on the norm-conserving shield potentials and variationally optimized numerical basis functions I will introduce later on. And the basic functionalities of the OpenMX are listed to the left here, and the extensions on top of the basic functionalities are listed here. So for the last about 25 years, we have been continuously developing the basic functionality and also the extension of the OpenMX code. So let me briefly explain the short history of the OpenMX code. So we have started the development of the OpenMX code in 2000, 25 years ago. And the first public release was made the 2003, 3 years later. So in terms of the GNU generic public license, and we have the many collaborators since the first public release. And then up to now that we have made the 19 public release. And the latest version is 3.9. So if you visit our website, so you can find the many informations. And you can download some sources, program package and other data freely. And this is the number of the code lines of the OpenMX as a function of the calendar years. At this moment, the number of the code line of the OpenMX almost 500,000. It's not small code anymore. It's very big code. So we are now planning to release new version 4.0 in this years. So this is the list of the contributors to the OpenMX development. So many Japanese researchers contributed a lot, not only in university, but also the companies, researchers, and also the other Asian countries, Koreans, and also Koreans, Taiwan's, China's, contribute a lot. I would like to thank all the contributors to this OpenMX development. So we regularly organize the workshops as shown here. We have organized 25 workshops so far. So here's I'm showing some typical materials studied by the OpenMX code. So I just mentioned a few. First, OpenMX was used for the first characterization of the silicon on the zirconium dibolide, which is in collaboration with the experimental groups. And also the OpenMX was used for the first identification of the J-effective half molten state of iridium oxide. And also many of the topological insulators are proposed, discovered by OpenMX calculations. And also the lithium-ion batteries simulations were conducted by OpenMX. And some permanent magnetic materials are treated by OpenMX. And also the electric transport of graphene nanoribbon on some surface oxidized silicons were treated. This is also quite big calculations. And some materials used for some steels are studied by the OpenMX code. So materials treated so far by OpenMX are listed here. And so far about 1,400 papers have been already published by using the OpenMX code. So let me briefly explain the basic algorithmic structure in OpenMX code to solve the quantum equations. So three-dimensional coupled nonlinear differential equations have to be solved self-consistently. So we have the eigenvalue problems here. But to solve these eigenvalue problems, we need to construct this matrix. The matrix consists of like this, which has the kinetic contributions and the potential contributions. And to construct potentials, we need to assume some certain initial guess of the charge densities. Then with this initial guess, we can construct the charge density and also the effective potentials. Then with this Hamiltonian, we solve the eigenvalue problems. Once we solve the eigenvalue problems, eigenvalues and eigenvector are obtained, and which are used to construct the charge densities of electrons. Here's these electron densities are plugged into the here's Poisson equations, and also the calculation of the exchange correlation potentials. Then we updated this effective potential to reconstruct the Kohn-Sham Hamiltonians. So this process are repeated until the self-consistent conditions is satisfied, which correspond to these conditions. Input charge densities is equal to the output charge densities. So until this condition is satisfied, we repeat these self-consistent loops. Typically, these loops takes 20 or 30, sometimes 100 iterations are required. And also the computational cost, computation complexity is written by these ones, red colors. This part takes the bottlenecks, order n cubic. Here is order n's. Here is order in log n's. And here is order n's. So main bottleneck is here, solving the eigenvalue problems. So to solve the Kohn-Sham equations, we have two very important practical issues. First one is how to expand the Kohn-Sham orbitals. So we have the two choices, localized pictures or delocalized pictures. The Kohn-Sham orbital psi need to be expanded by the basis set chi's, just like this. So as I mentioned, we have two choices, localized basis shown here, delocalized basis set shown here. So based on these ideas, actually the developers around the world choose one of them's localized picture or delocalized picture. But basically the localized pictures and delocalized pictures can be converted by the unitary transformations. So OpenMX case, we use localized pictures from here. Okay, then the actual implementation is much more complicated. So our method is LCPAO method, linear combination of the shared atomic orbital method. So one particle Kohn-Sham orbital is expanded like this. So linear combination atomic-like orbitals. So here is the basis function chi's. The chi is given by the product of the spherical harmonic function times the radial function R's. So this atomic-like orbitals following good features. So it is easy to interpret the physical and chemical meanings since the Kohn-Sham orbitals are expressed by the atomic-like basis functions. So it gives the rapid convergent result with respect to the basis function due to the physical origins. The memory and the computation effort of the calculation of the matrix elements are linear scalings. So actually this radial function takes the following shapes. So this is the carbon atoms, s orbital and p orbitals. Another important practical problem is how to treat the core electrons. So this is the electron structure of the silicon bulk. So then the silicon atoms have many electrons, starting from the 1s electron to the 3s and 3p electrons. And I'm showing that the eigenvalue energy of each state. 1s state is situated at the very deep state, around the 1700 electron volt. And the electronic wave function of the 1s state is highly localized, shown here. So since the core electrons are situated at the energetically very deeper state, they are inert chemically. In molecules and solids, they do not change so largely. So based on these ideas, the pseudo potentials actually replace the original very deep nucleus potential by the soft effective potentials. So this is the idea, basic idea of the pseudo potential theories. So OpenMX also employs these pseudo potential theories. The actual forms as a bit complicated formulas shown here. OpenMX employs the norm-conserving Vanderbilt pseudo potentials. So following the non-local operator proposed by Vanderbilt guarantees that the scattering properties are reproduced around the multiple difference energies. I'm not going to inside of these techniques, but if we introduce the project formulas for the pseudo potentials, actually this reproduce the scattering properties very well, which are well compared to the original scattering property of the original deep nucleus potentials. So replacement of the very deep nucleus potential to the shallower pseudo potential is extremely important to make the calculations very fast and efficient. Another important practical issue is how to parallelize the code quite efficiently on the parallel computers, massively parallel computers. So how one can partition the atoms to minimize the communication and memory usage in the parallel calculations. So we actually developed the very nice ways, and this atomic 3D atomic partitionings should have the following requirement: localities in real space, and the allocated atoms should have the almost same computation cost, and the methods should be applicable to any systems, one-dimensional system, two-dimensional system, and three-dimensional systems on the equal footings. And this method should have the very small computation overhead. So our method is the recursive atomic partitioning method. So we have some certain systems, in this case, the molecules. So we calculate first the principal axis. Then on the principal axis, we project it onto this principal axis. Then the three-dimensionally distributed atomic positions is now one-dimensionalized. Then it's easy to decompose left to right. So left to right. And then hold each decomposed partitioned systems. We again calculate the principal axis shown here and project it onto this principal axis. Then one can decompose again like this. So this is the recursive atomic partitioning method. So I would like to show the examples how these partitioning techniques allocate the atoms to the MPI process. So this is a diamond structures consisting of about 16,000 atoms. And I employ the 19 MPI process, which is the prime numbers. So I use the prime number intentionally. Then, as you can see, same colored atoms are allocated to the same MPI process. So atoms are allocated very compactly, just like this. And also we can expect that the communication amount is actually minimized. And also the computation cost for each allocated regions may have the almost equivalent computational cost. So this is another example, multiply connected carbon nanotubes with the 16 MPI process case. So another difficult problem is how to partition the grid. because we need to solve the three-dimensional differential equations. So we need to introduce this kind of the real space grid. Then how to treat the real space grid and how to partition to the MPI process is a really complicated problems. And we introduce the whole kind of the data structure A, B, C, Ds. Then on top of the whole structures, data structures, we develop the very nice kernel structures. So actually calculations start from A, go to the B, and change the C, and again return to the B. This allow means that we perform the MPI communications. The actual calculation can be performed by just following the ABCs or the calculation charge densities. The other is also same, just like this. So they are actually designed to minimize the MPI communications. And these data structure are all constructed in this subroutines and also these ones. And also the OpenMX has a very special techniques to parallelize the three-dimensional FFTs, which has the smallest communication amount compared to the other method. So we developed our own method and implement it into the OpenMX code. And we considered this kind of the partitionings on the AB planes. So P1 region is allocated to the MPI process ones. P2 regions, P2 here are allocated to the MPI process twos. Then we perform the one-dimensional FFT along the C directions. Then after finishing all the one-dimensional FFTs in each MPI process, so we need to change the direction of the FFTs. So in this case, we change from C to B's. Then we need to perform the MPI communications. And then from here to the here's, we would like to minimize the MPI communications. So we analyze quite carefully. Then we notice that our decomposition method has the smallest communication amount compared to the other proposed method. So this is one benchmark calculation to check the parallel efficiency on K-compute. This is a little bit old studies, but it actually clearly shows the good parallel efficiency of the OpenMX code. So in this case, we perform the very big diamond structures about the 131,000 atoms. And parallel efficiencies was found to be the 68% using the same cores. So this number is equivalent to the number of the atoms shown here. So then let me say a couple of things about the basic structure of the OpenMX code. So OpenMX codes have the following features. These codes are written mainly the C language, very basic C language, and some part is written by the Fortran 90s. And OpenMX has the 434 subfiles and about the 2,000 subroutines. And also this code has 39 header files, and it has 500,000 lines. And compilations can be performed by makefiles. And also the eigensolvers, OpenMX eigensolvers, we implemented the ELPA into the OpenMX code itself. We modified a little bit ELPA original code. So distribution package of the OpenMX includes ELPAs, modified ELPAs. And OpenMX needs to linking to the array pack, BRAS, FFT W3s, BRAX, and SCA array pack. And hybrid parallelization by MPI is OpenMP implemented in OpenMX code. And this is the basic computation flow in OpenMX code. So main computation flows is controlled by the subroutines OpenMX, and input standard STDs. These are the input files, analyze the data structures, and truncations subroutines analyze the geometric structures, memory allocations, handle the memory allocation, analyze the communication patterns. The subroutine DFTs perform the SCF calculation, total energy, and Horst calculations. And MD-PAC performs molecular dynamics and geometry optimizations. And after the calculations, data are output in this output data subroutines. And OpenMX command.h, this is actually in this header files, common functions and common variables are declared in these header files. So let me briefly explain the one applications. So this is a collaborative research to identify the silicon structures, which is a honeycomb structure of the silicon atoms. And the collaborators is shown here, experimental groups and the simulation groups shown here. And some of you may know the recent emergence of the new two-dimensional materials like graphene, silicon, hexagonal boron nitride, and transition metal dicarbonate systems. So we also conducted such materials, and I participated in the collaboration to first identification of the silicon structures. So Professor Yamada Takamura group of the JIST first fabricated the silicon structure on the zirconium dibolide. So they are trying to make this kind of the device. Then they check what kind of structures emerge on top of the zirconium dibolide before making this gallium nitride thin films. Then they accidentally discovered interesting structures shown here. This is a scanning tunneling microscopy image. Then by magnifying these pictures, they found honeycomb structures. They are very much excited because this atom seems to be silicons. So therefore, the honeycomb structure of silicon seems to be homed on top of the zirconium dibolide. So we actually collaborated and performed the geometrical optimization on top of the zirconium dibolide. Then we got the regularly backed structures shown here and planar-like structures. So we have the two kinds of the stable structures from the calculations. So this is the side views. So this is a regularly backed structures. This is a planar-like structure. As you can see, the backling structure is very different. And compared to the binding energies, from the theoretical point of view, planar-like structure seems to be ground state structure. This has a 1.42. So larger means that more stable structures than the regularly backed structures. So we tried to propose the planar-like structure to experimental groups, but they prefer the regularly backed structures because the regularly backed structure is almost equivalent to the 111 surface of the silicon diamond structures. So therefore, they try to stick regularly backed structures. We did a lot of the calculation and compared the experimental data. Then the one striking the data agreement was found in the calculations of the X-ray photoemission spectroscopies and the experimental data. So this is the experimental data of the XPS, X-ray photoemission spectroscopies, taken by the Yoshinobu laboratory in our universities. So we noticed that the three peaks, alpha, beta, gammas, and we performed the XPS photo spectrums calculations based on density function series for the backed structures shown here, and the planar-like structures shown here, and compared to the experiment. Then we noticed that the planar-like structures simulation data is well compared to experimental data very well. Then we reach the conclusions. In the early speculations, regularly backed structure was supposed, but the DFT calculation of the angle-resolved hot emission spectroscopy, Honon's and X-ray hot emission spectroscopies strongly support the planar structures, these structures. So we now concluded that the experimental structure is the planar ones shown here. So let me move on to the student cluster competition part. So for this the remote competition part, OpenMX part, we prepare the two input files. One is the 1-methane dot. This is the for the SCF calculation of the methane molecules. A very tiny input for the teams to check if the application OpenMX code works or not. So it's very small calculations. The second one is actually the student competition input files, 2-NVC dot. This is for the SCF calculation diamond NV centers, nitrogen vacancy centers. So this will be used for the remote competition part. So using the small input files, you can perform the SCF calculation of the methane molecules based on the density functional theory within the generalized gradient approximations. So calculation takes only a few seconds, even using the just single cores. Only, I guess, 5 seconds is enough to get the convergent result. So after the calculation finished, met.out is generated in your directories. By comparing the numbers in methane out with those shown below, I'm showing my calculation result, one can confirm if the calculation performs normally or not. So if the last 7 digits are first 7 digits are equivalent, then we consider that your installation, the calculations are successful. After calculation finish, a cube files, .cube files is generated, and by dragging and dropping it on the OpenMX viewers, the following figure is obtained, shown here. So this is the isosurface map of charge densities of these methane molecules. The second ones, so using these files, one can perform the SCF calculations of the diamond with nitrogen impurity and its neighboring vacancy, called the NV centers, based on DFT within the GGAs. So NV centers have this kind of spin densities, and people consider that this localized spin can be used as the quantum qubit for the future quantum computers. We will try such calculations. And after calculations finished, this out files is generated. And comparing the numbers in this out files with those shown below. So this is my calculations. One can confirm if the calculation performed normally or not. So if you notice that at least the first 7 or 8 digits is equivalent to your numbers, we consider that your calculations is successful. So after calculation finished, the cube file is generated, and by dragging and dropping it on the OpenMX viewers, the following figure is obtained. So this is isosurface map of spin densities. Here is the vacancy site. Some blue colored atoms is the nitrogens, and the neighboring the carbons are some spin densities. So actually these 3 atoms have a dangling bond, which possesses the spin densities. So a SCF calculation of these NV centers was achieved at the 37 iteration as confirmed in this out files. So this is my calculations. So you can compare your calculations, whether your calculations converged in similar ways or not. And this one is benchmark calculations, MPI parallelizations. So this benchmark calculation was performed in our supercomputers, Otakas, installed in the University of Tokyo. So by changing the MPI process from the 64 to the 500 to the 12, so elapsed times of the total, this is the total elapsed times change, just like this. So you can also compare your benchmark calculations. So, and also the elapsed time of each routine of each MPI process can be confirmed in this out files as shown here. So in this out files, you can find the following informations. So this is the elapsed times of each routines. And this ID means the MPI process IDs. So therefore, in this case, MPI process IDs 111 computation time was the 2.385 seconds. So by looking carefully at these data, so you can try to minimize the computation times by changing some compilation options, or someone may try to improve and modify the code itself. So developers versions 3.962 will be used for the student competitions. How to compile is shown below. I don't say it anymore, but you can follow these ways. If the compilations is successful, you define the executable files OpenMX in the directory OpenMX 3.9 work. So please try. And also we have our own viewers. Because the cube files and other zip files, XYZ files is commonly used worldwide. Many software packages support this kind of the files. But OpenMX Viewer also supports this kind of files. And if you drag and drop those files on this website, then you will see the structure of your models, and you can analyze step by steps. So other informations can be found the following website: the manual of OpenMX, data structures of OpenMX, and a theory of the OpenMX implementations, and a theory of DFT and the related issues, and a method of parallelizations, and a list of publications to which the OpenMX contributed are found at this link URLs. So if you are interested in please visit theirs. So let me almost the times. So let me summarize my talk. So computational materials science is one of the most relevant fields directly affecting our daily lives. DFT plays a versatile role in investigating the physical and chemical properties of the materials. So OpenMX is an efficient implementation of the DFT that has been developed especially within the Asian communities. I hope that you will become interested in this field through these competitions. So thank you very much for your kind attention. If you have any question, please.
Thank you very much, Professor Ozaki. It was a very interesting and deep presentation. Let's open for questions if you have any. Of course, you can always also ask us on Slack, and if you have any issues along the time, I will try to support you. Yeah. Someone is asking about GPU version. I'm not sure if available, but it's not required. Is it available?
No, it's not available. So we
Not available, yeah.
internally though we have been developing, but it's not released yet, and this will not be used for these student competitions.
Thank you. Good question. Anyone has any other questions? Yes, just Hans Nozaki, you want to say something?
Yeah. Hello, everyone. My name is Nozaki. Can you hear me clearly?
Yeah.
Okay. Hi, Mr. Ozaki. So, I read a bit about OpenMX manual prior to this, and I got a bit curious because earlier you explained how each MPI process will map into each atom. So then, in case where the number of process is more than the number of atom in the data, how exactly did that map, and how exactly did that impact the performance of the OpenMX?
Yeah. So we have the hierarchical structures for the parallelizations. So if the number of the MPI process exceeds the number of the atoms, then we go to the lower levels. So, but for example, the conventional bundle structure calculation, we have many parallelisms. One is the K-point parallelization, other is the spin parallelizations, and also one more thing is the eigenvalue parallelizations. So we have the many kinds of the parallelisms. So therefore, we have the hierarchical structures. So in the case that the number of the MPI process exceed number of the atoms, then we go to the lower levels step by steps. We develop such hierarchical structures for the MPI parallelizations.
Okay. And does that parallelization happens for all type of that input data, or will it only apply for when you declare it explicitly in the data set?
No.
The input data?
OpenMX automatically recognizes the situations and try to find the best ways automatically. User is not required to specify anything. User only have to specify just the number of the MPI process, the number of the OpenMP thread. That's all.
Okay, that's very cool. Thank you so much for your time.
Malte, you wanted to say something? I saw a question on the chat.
Well, I couldn't read the chat.
Can you find the chat? There was a question from Malte Kunz.
Could you read?
You showed the two NVC output was that nvc.dden.cube or nvc.sden.cube. nvc.dden.cube.
Yes. Maybe I made a mistake. So after the calculation, we have many cube files. Some of them is the spin densities, other is total electron densities, and the potentials, and wave functions, and they are also explained in the manuals. Maybe this statement is a bit. I mean, this should be not the DDENs. This SD should be S.
It should be SDDM?
Yeah.
SDM?
Yeah, I think so. So this should be S. Yeah.
Oh. Thanks for the clarification. It was a good question, Malte. Anyone has any other questions? Any other questions? Okay. So one comment from my side, this application is should be tested only on the Bridges 2 clusters, not on the DKRZ cluster, right? Just to make sure. And up to test on four regular memory nodes, RM nodes. So if you have any cluster issues or connectivity issues to allocate, let me know. You should all have access by now. Any additional questions? Yeah, I see another question. Would using OpenMP also improve performance? This was a question.
Yeah, some certain machines, best combinations lead to the very smallest elapsed times, I guess. But it depends on the systems we calculated and also the system for the computational machines. I cannot say the best combinations at this moment.
Yeah, I think it's something you can explore and see if that gives you better performance on the actual clusters. In many cases, different applications will see that it helps, but again, depends on the application and the distribution of the problem across the nodes.
Yes.
Anyone has any other questions? Okay, so I would like to thank Professor Ozaki for the very nice presentation and for the support, as I think really helpful. And I will be listening on the Slack, and Professor Ozaki also on the Slack, and one other member, right? I forgot who, also from University of Tokyo. We will try to support you with any questions that will come up or may come up along the way. And later on, around May, right, end of May, we'll have team interviews, and starting on May 12 and May 19 this week, like mid-May time frame. I will still have time, so I will try to assign it later on. I will let you know about that, but that will come up later on. And besides that, good luck. And we'll have today another 2 sessions. One that will start within an hour and a half, so 8:30 Pacific time, with Code Saturn, and the other one on SASOL 9:30, just after that, 9:30 Pacific time. So based on your location and the team location, just calculate the times. And again, good luck, and thank you everyone for joining. Okay.
Well, thank you very much, Ophirs.
Bye-bye, everyone.
All right. Thank you.